Hello and welcome. We live in a time in history that has long been given the name the Information Era. It's a time in global history in which humanity has been given access to more data and analytical techniques than any time in, of course, global history. However, until recently, most of the techniques involved in analyzing such data, as well as even the availability of the data itself, has usually been in the hands of a select elite few, until recently. With the advent of the internet, combined with some prolific software packages such as Microsoft Office, as well as some freely downloadable analytical programming languages like Python and R, which have allowed the process of analyzing and accessing data to become democratized and available to all people. Now, a complete discussion of all the different analytical techniques available when you do statistics is well outside the scope of this class. But suffice it to say, we can at least describe two different types of statistics that we can create to describe a certain data set. And they fall into two categories. The first one is called measures of central tendency. If you have a lot of data, a measure of central tendency tends to give a kind of epicenter that summarizes where all the data is. And a second type of statistic is called a measure of dispersion. And that gives an indication as to how widely spread out from that central epicenter all of those data are. So that's what we're going to be discussing today, but let's first take some time for ourselves to bring ourselves completely into the now, to become completely awake. Take some time for yourself. Welcome back. Let's get right to it. I'm showing you here two groups of data, one on the left, one on the right, each of them having two columns. And perhaps these data describe heights of individuals in centimeters. Well, when we're dealing with two different groups of data, one is tempted to describe which one of the groups generally has larger people. In this case, which sets of people are taller than the other. And if you take a look at both of those sets of data there, perhaps it's pretty straightforward to be able to say that the heights that are shown in the right half are larger than the ones that are shown on the left side. The ones on the right seem to be consistently above 200, and the ones on the left seem to be consistently below 200. So in this case, it's pretty easy to see which set of values is larger. But I'm going to show you another example here in which it might not be so easy to see which set of values is larger, the one on the left or the one on the right. When I take a look at these two sets of data, most of the values on the left are in the 100s. Most of the values on the right are also in the 100s. It might be difficult to tell exactly which set of values is larger. Hence, some of our measures of central tendency. And one of them, one that you are most likely already aware of, has to do with finding an average. And the way that we describe finding an average here is that I'm not only describing this with one variable, but you'll notice that I'm assigning each value in those two columns a value of x. So they're all given the same letter here. I didn't want to have to make use of multiple letters here. But in the lower right-hand corner, for each one of these variables here, you can see the numbers 1, 2, 3, 4, 5, and so on. Now these are numbers that are in the lower right. They are not exponents. They're just part of the label. So each one of these variables might be called x1, x2, x3, and so on. And they are numbered in this case all the way up to 30. We have 30 data points for us to find an average of. Well, how do we find an average? You might already be aware that the way in which we find an average is we add up all the numbers and then divide by the number of numbers. In this case, we're adding up all of the numbers from x1 to x30 and then dividing that by 30. Now perhaps it's better to say that in general, the way that we find an average, if you were going to write down a general formula on how to do this, then we don't want to assume that there are 30 data points. So let's generalize this by saying that in this case we are going to be adding up all the numbers from x1, x2, and so on and so forth. That's what those three little dots indicate, all the way up to the last one, x sub n. So in this case, n is the number of data points that we're working with. So adding them all up would be x1 plus x2 plus and so on, all the way up to adding the last one, which is x sub n. When we're done with that, we divide by the number of numbers, which in this case is n. So that's a nice general formula that will always work when finding the mean. The mean and the average are the same thing, by the way. So we can use either term. So in this case, we add up all those numbers there and we get 4,922. We divide that by 30 to get a mean of 164. For the other set of values, we add them all up. We get 5,424. We divide that by 30 and we get a slightly larger number of 181. And so as we bring back these two sets of data once again, we can now compare the means. We can now compare the averages. The data set on the left shows an average value of 164. The set of data on the right has an average value of 181. So that immediately indicates that as a whole, the numbers in the right-hand set of data, the second set of data, is larger than the one that's on the left here. We've defined a measure of central tendency, namely the mean. But that's not the only measurement that we have of central tendency. We have two others to also be aware of. The second one is known as the median. Now the way in which we define the median requires an extra step here. So we're looking at this right-hand set of data once again. You'll notice that I've done something a little bit unusual with these data, and that is I've ordered them from the smallest value all the way up in those two columns to the largest value. So the smallest value is in the first place, which is 113. The largest one in the bottom of the second column there is 197. So I've placed them in order. The median is the middle value, the middle number in that range there. It's the number, it's the data value at which you find half of the data being less than you are and half the data being greater than you are. In other words, if you have the median, if you are of the median age in your town or city or community, that would mean that you are older than half the people in your town and you are younger than the other half of the people in your town. So you're right in the center here, with half being older and half being younger. In the same way, the median number here is right in the center here. Now, we don't actually have a middle number here because we have an even number of data points here. So what we have to do is take the two that are in the center here, in this case 166 and 169, and we have to add those two together and divide by 2. We're essentially finding the mean of those two that together form the center of the data. Well, 166 plus 169, dividing that by 2 gives us a median of 167.5. So half the data in these two columns is less than 167.5, and half the data is greater than 167.5. That's the median. The third measure of central tendency that we have is called the mode. And to figure out the mode, it's also of some value to place all of the numbers in order from smallest to largest, because what you want to do in order to find the mode is essentially find what are the data values that are most popular. And if I take a look here, I can see that there are 138. The value of 138 appears 3 times. The value of 169 also appears 3 times. And the value of 171 appears 3 times. So sometimes when you're doing these kind of analyses, you find one data value that seems more popular than any of the other ones, and that data value is your mode. There are other times when you're doing these kinds of analyses and you find there's a tie for first place as far as 2 data values that are the most popular. That's a bimodal distribution, bi meaning 2, and so you have 2 modes to contend with. In this case, we've got a 3-way tie, so this is a trimodal distribution, and so we actually have 3 modes to work with here: 138, 169, and 171. There are also instances in which there isn't any clear value that emerges as being the most popular, and in that case there is no mode for this set of data. So it's possible for there to be a mean, a median, but no mode of a given set of data. So we've done that for the first set of data. If we do this for the other set of data to compare it to, we have 2 middle values once again, but they're the same value, 180, so finding their average is pretty easy. So our median is easy to calculate here. It's just 180. And our mode is also 180 because the number 180 appears 1, 2, 3, 4, 5 times. That's more than any of the other data values in there. And so in this case, the median and the mode are the same, and we have a single mode. It is a unimodal distribution. So let's put all of this together. We're showing the 2 data sets here once again, the one on the left, the one on the right, and as we can see, the mean of the one on the left is 164, the median is 167.5, and there is a 3-way tie for the mode. There's 3 different modes: 138, 169, and 171. The measures of central tendency for the data set on the right is a 181 for the mean, and there's a value of 180 for both the median and the mode. That is, those are consistently measures of central tendency that are greater for the set of data on the right than on the left. So as a whole, the set of data, the set of values that are larger is the set of values that are on the right. So take some time to do this yourself here. I've got 3 different sets of data there. There's pulse rates, where I've got 6 pulse rates. There are 5 different weights in pounds there, and there are 4 different temperatures. Calculate the mean, the median, and the mode for each one of these. Take some time to do that. Welcome back. Well, hopefully this gave some good Welcome back. Well, hopefully this gave some good practice for your newfound skills here. In this case, we have a pulse rate mean of 76.7, a median of 78. That's the average of those two in the center there, 76 and 80. And the most popular value, the mode, was 80. The weights in pounds, the mean was 26.9, the median was 33, also the mode being 33. And lastly, for those temperatures, we had a mean value of 58, a median value of 59, and there was no mode this time. Now notice I rounded to the nearest tenth in some cases here for calculating the mean. That was just my own. There wasn't any particular reason for that, I just did that. Now, why would you think that we would have multiple different ways of describing the epicenter of the data? Well, we have three different tools, as you've seen, and there are instances in which one is actually better to use than another. Here's an example of one. Let's say this is a set of home values in a particular neighborhood in Fort Collins. It's a set of house values there ranging from 195,000 all the way up to, well, near the bottom there we have 575,000, but then we have this bottom one here, $2.7 million for this one house. Perhaps this is a cul-de-sac with one very expensive mansion at the very, very end of the cul-de-sac. Now, if we calculate the mean for each one of these home values, we get a value of 649,000. When we calculate the median, we get 428,000. And so the question here is, which one of these values is more meaningful? They're both correct mathematically, but which one of them describes the data in a more effective manner? Well, one of the things that I notice is that when I look at the mean of 649,000, there really aren't any houses on this cul-de-sac that have a value near that value, 649,000. They go all the way up to 575 and then all of a sudden jump to this much higher value here. But if I take a look at the median, 428,000, well, yeah, there are quite a few houses that are well represented by that measure of central tendency. And so in this case, the median is actually more descriptive, more meaningful as far as describing what's going on here. This is actually why whenever we're describing things related to income, including income levels, we almost always describe things in terms of the median, because much like what you're seeing here, there's usually a set of low income values and then moderate income values, and then way off in the middle of nowhere we have the Bill and Melinda Gateses who kind of throw the mean off into this area that is not very well represented. And so usually median incomes are what are reported for each given community, each given state, and so on and so forth. Now let's take a look at how some of these different measures of central tendency can sometimes interact pretty interestingly with each other. And I'm showing you two different classes here, and I'm showing with each one of these the number of inches tall each one of these individuals is. And we're asking the question, which class is taller? Well, if I calculate the mean for each one of them, I have values of 43 and 45. Interesting. But if I calculate the median, I have 45 on the left and 34 on the right. So interestingly enough, when I take a look at the mean, then the class on the right actually would be considered taller. But if I look at the median, then the class on the left would be considered taller. So which one is right? And so that's something to keep in mind here. Sometimes we are finding averages when we don't even realize that we're finding averages here. Here's an example. Let's say I drove from Fort Collins to Colorado Springs in 2.5 hours, and this was a total distance of 125 miles. So I could ask myself, how fast was I going overall? Well, that would just simply be 125 miles in 2.5 hours. I do that division problem, I get 50 miles per hour. But it's pretty obvious to say that I'm sure that I wasn't going 50 miles an hour every step of the way from Fort Collins to Colorado Springs. There was probably some stop signs that I had to hit, or maybe some traffic jams, or some places along Interstate 25 in which I could cruise at a much higher speed limit than 50 miles an hour. The point is that when we're making these kinds of calculations, which many of us make all the time, we're actually implicitly calculating an average. And so you might actually be calculating averages far more frequently than you realize. Now, unfortunately, there are many different ways to calculate an average. And a good example of this has to do with the calculation of grade point average at most schools here. Let's begin with the non-weighted average, which we're already familiar with. And let's say this is a person's report card here. This person took, looks like 5 classes, Algebra 101, Welding 102, Literature 301, History 101, and Basket Weaving 101. And they got grades of B, A, C, and A. Okay. Well, usually what happens when we do this is we assign each one of those grades a kind of point value, and you can see that in the 4th column over the points. So B's have a point value of 3, A's have a point value of 4, C's have a point value of 2, D's have a point value of 1, F's have a point value of 0. And so as we assign those points, we can then, in the last column, simply add up all those points and then divide by the number of classes. And the result there is a grade point average of 3.4. That's a kind of B plus, A minus kind of average there. So that's the non-weighted average. But oftentimes schools like to use not that kind of an average, but a weighted average, because when you take a look at those 5 classes there, especially considering that Basket Weaving 101 is only a single credit, and so probably met maybe once a week or so for an hour, and was almost certainly not as intellectually or academically rigorous as, say, History 101 that was a 4-credit class, and so met far more frequently and for longer periods of time, and certainly involved a lot more work than Basket Weaving 101. It seems reasonable that the C, unfortunately, for History 101 should have a slightly greater weight to it than the A that the person got in Basket Weaving 101. And so here's how this is done. Same grades, same point values for each one of those grades, but we now are taking a look at the credits associated with each one of these classes. And the first 3 classes all have 3 credits. The History 101 class must have been quite a bear. It was 4 credits rather. And lastly, Basket Weaving 101 is just 1 credit. What we do is we take each one of those point values and multiply it by the number of credits. So on the top line there we have we have 3 credits multiplied by 3 points to give us 9 total points. In the second row we've got 3 credits times 4 points. That's 12 total points. And we keep doing that for the other 3 classes. And in this case now we add up the total points and we get 45. Now, what do we do at this point? Do we divide by the number of classes? No. When you have a weighted average, you don't divide by the number of numbers. You divide by the total amount of all the weights. Well, what were we using to weight all of these grades? Well, we were using the credits. So what we do in this case is divide by the total number of credits. And in this case, that was 14 credits. That's all of those credits add up. So we now take 45 and divide it by 14. And we get a grade point average that is a little bit lower, but perhaps more emblematic of the actual amount of success that this person had over the course of the semester, because it weights more heavily, rather, the grades that a person got on the classes on which that person was at least supposed to spend most of his or her time. This is a GPA now of 3.214. So on the topic of grades here, let's actually take a look at an example of this sort of thing. Sometimes you can work with the formula for averages to try and kind of work backwards on figuring out what kind of grade do you need to have on a given test or exam in order to get a desired average grade. Let me show you what I mean here. A student has the following exam grades in Physics 101, 73, 84, 80, 62, and 70. And there's one more exam to take. The student desires to have a total exam grade average of 75. What grade must the student get on the last exam in order to achieve this? Well, what we're doing is we're setting up the exact same formula for doing an average here. In this case, this is a non-weighted average. So we're counting each one of these exams exactly the same. There's no weighting associated with it. So we're just adding them all up and dividing by the number of exams, which is 6. But notice there's a variable up there. One of the exams we haven't taken yet, and so it's an unknown grade. But when we add all of those up and divide by 6, what we desire to get is 75. Well, we now have an equation that we haven't really talked much about equations yet, but perhaps you can see that I'm eventually going to solve this to find out what x is. And the way that we would solve this is by, first of all, adding up all those numbers there to get 369. So you can see that in the lower left-hand corner. I've simplified this a little bit, so this is x plus 369 divided by 6 equals 75. So we don't know what this exam grade should be, but we do know that when we add 369 to it and then divide by 6, we want to get 75. Well, on the left-hand side, I want to get x by itself so that it's easy to see what x should be. And the first thing I want to address is dividing by 6. The opposite of dividing by 6 is multiplying by 6. So I'm going to multiply both sides of this equation by 6, and that makes that division by 6 disappear on the left-hand side. On the right-hand side, I multiply 75 times 6, and I get 450. Now all I've got is whatever number this exam grade should be. If I add 369 to it, I should get 450. Well, perhaps you can discern what number that is here. But if I subtract 369 from both sides, then all I have is x on one side, and on the right side I now have 81. So we've just discerned that in order to get a 75 average on all of the exams, this person has to get an 81 on the last exam. Now sometimes when we are dealing with data, there's a certain amount of confidentiality that's desired, or there's a certain desire to not describe it in exact increments, but to describe them in terms of grouped sections. This happens in many different situations here, but in this case, let's say it's because of privacy concerns. So we've got a set of test grades here that are listed in their raw form in the left-hand side there. We want to keep those confidential. And so what we're going to do is instead report the grades in this chart above my head here, which is, it shows a series of ranges. The first range is from 60 to 64. The second range is 65 to 69. Third is 70 to 74, all the way down to 95, all the way up to 99. And you can see in the second column there's a tally of the number of students that were in that had grades in each one of those class intervals. So apparently there was one student who had a grade that was somewhere between 60 and 64. And there were 6 students who had a exam grade that was somewhere between 75 and 79. So that tally shows the most popular data range values there. Now if I take a look at each one of those class intervals there in the first column, 60 to 64, well, what's the middle of that column? Well, the middle of that column, the middle of those values rather, would be 62. It's halfway between 60 and 64, so I might say that the midpoint of that range there is 62. So what I can do is I can still calculate the average value for all of these students here, but what I'm doing is instead of looking at the raw data, which perhaps I don't have access to, I'm looking at all of these class intervals and I'm representing each test value as being the same as the midpoint. So in this case, you can see in the first row there, I'm assuming that the grade that this student had, this one student had in that tally, was in fact 62. And if you scroll down 3 more rows there, I'm assuming that all 6 of those students that had a grade somewhere in the 75 to 79 range in fact had a grade of exactly 77. So I'm representing them using the midpoint of each one of those ranges. So in the rightmost column here, I'm sort of tallying up all the points for each one of those ranges. One student having a score of 62, that's 62 points. Another student in the next row having a score of 67, that's another 67 points. Now I've got in the third row 2 students that are both assumed as having scores of 72, right in the middle of that range, and so that contributes another 144 points to the average, and so on and so forth, all the way down to the bottom there, where we total up all those points to get 2,070. And if I divide that total by 25, I get 82.8. And if I actually compare that to the real average of all the raw data, which is 83.1, so give or take, that's a little off, but fairly close. So you lose a little bit of accuracy when you summarize the data in this format, but perhaps if you don't have access to the raw data because of privacy concerns or for other reasons, this is better than nothing. So that's another different kind of average that's available to you. We've talked about the non-weighted average, the weighted average, and the kind of average that you can make of group data, where you're working with data that's been classified in intervals like this. Another thing to point out is that when you take a look at each one of these intervals with the tallies that you see of the number of people in each interval, this is called a frequency distribution, and we can use this to answer quite a few questions about the data. For example, how many students scored 70 or higher? Well, when I take a look at all of these rows here, I notice that let's see, the first row, that student had a score somewhere between 60 and 64, so that student doesn't count. 65 to 69, that's another student doesn't have a score of 70 or higher. But the third row and all the other students in the subsequent rows, those are students who had scores of 70 or higher. So it looks like all but 2 of the students, in other words 23 students, had scores of 70 or higher. And you can see that you can pull that information pretty easily off of a chart like this. How many students made A's, in other words having a score of 90 or higher? Well, I'm seeing 2 different rows here, one showing a range of 90 to 94, that's 5 students. Another one showing a range of 95 to 99, that's 2 students, for a total of 7 students who made A's. And so what percent of those grades would be A's? Well, that's 7 out of 25. That would be actually, I believe, 28%. So do this one on your own here. Students in a math class reported their credit hour loads this semester, and again, to protect some privacy, exact numbers were presented in terms of class intervals, which you can see in this chart above, along with the number of students in each category. So answer these questions for me. And these are specific to the kinds of things that we were looking at in just the previous slide here with frequency distributions. How many students have a load of 10 or more credits this semester? Also, what percentage of students have a load of 10 or more credits this semester? Also, estimate the mean number of credits using the midpoint of each class interval. So take a look earlier in the video, how do you find that midpoint, and then how do you figure out the total number of points for each one of those students in that interval and add up all those points to figure out what your average is. And then lastly, estimate the median. See how you would do that. I didn't really talk about that, but I'll bet you can figure it out based upon the data that's sitting in front of you, which if you put the data in smallest to largest, as it's shown there, can you figure out where the median should reside? So take some time to do all those problems. Well, in this case, we have our first question being addressed by the latter two rows here, 10 to 14, the class interval there having 4 students in its tally, and then the row 15 through 19 having another 2 students in its tally. 4 plus 2 is 6. And to answer the second question here, those 6 students out of 16, 6 divided by 16 is 0.375, which is 37.5%. So we're making use of some of our percent discussions from some previous videos there. Estimate the mean number of credits. Well, we first find those midpoints of each one of those class intervals there. From 0 to 4, the middle value there is 2. From 5 to 9, the middle value is 7. And the other two are respectively 12 and 17. We then take each one of those tallies and multiply those tallies by the midpoints. So 3 times 2 is equal to 6. That's the first value. Second value, 7 times 7 equals 49, and so on and so forth. We then add up all of those points to get 137. We divide by a total of 16 students to get 8.56. So that's our average, our estimate of the average at least, for the number of credits being taken by each student, the average number of credits being taken by each student this semester. And then lastly, the median number of credits. So how would you do this? Well, if you recall, in order to find the median, you have to arrange the data values in order from smallest to largest. And as you can see here with this frequency distribution here, we've sort of implicitly done that. We're showing the smallest ones on the top, the class interval of 0 to 4. We've got 3 students there. And so, and as we move down, we're getting the students that have the higher and higher amounts of credits there. So we have put these things sort of in order. The question is, we have 16 students, so what data value is in the middle? Well, 16 is even, and so it's really between the 8th and the 9th value that we would find the median there. So where would we find the 8th and the 9th value if we placed all of these data values in order? Well, we have the first 3 in the first row there, 0 to 4, and we have the next 7 students in the second row there. 3 plus 7 is 10. So the 8th and 9th values must be in that second row. So we can estimate that the median value would be 7, the midpoint of that class interval there. So the median number of credits we've estimated as being 7. Slightly less than that average value that we're seeing there of 8.56. So here's some summaries to describe exactly how you calculate each one of these measures of central tendency here. We've covered an awful lot of stuff here. There's mean, median, and mode, and then there are different kinds of means that we can calculate here. So let's first of all do the mean. I've got a nice little formula there where you add up all of the data values on top from 1 to n, n being the number of numbers that you're working with, and you divide that by the number of numbers. That's n on the bottom. And so using the same colors, I've got add up the quantities on top and divide by the number of quantities on the bottom there. To find the median, we arrange the quantities from smallest to largest. We've done that a few times today. And if the number of quantities is odd, then the median is the middle number. And if the number of quantities is even, now you have to find the two values that are in the center and average the two of those together. That's how you find the median. Lastly, the mode. You find the value or values, could be more than one, that occur most often. This could be a tie between 2 or 3 or 4 or 12 or whatever. And if no value occurs more than any other value, then you can say simply that there is no mode. And lastly, it is possible, as I hinted at earlier, for there to be multiple modes if ties occur with counting occurrences. So 2 or 3 might be tied for first place, so to speak, as far as popularity is concerned. And so it's possible for the data set to be not monomodal or unimodal, but to be bimodal, trimodal, and so on and so forth. Different kinds of means. Let's first of all look at finding the weighted mean. To find the weighted mean, well, hopefully, let me backtrack and say that the non-weighted mean is the formula that you saw on the previous slide there. So you've got the formula now for the non-weighted mean, but for the formula for the weighted mean, or the procedure for finding the weighted mean, is to first multiply each value by its weight. By the way, this is how your grade, your final grade in this class is calculated. It is a weighted mean of 4 separate percentages. Your class participation percentage, your homework percentage, your exam percentage, and then your final exam percentage. So those have specific weights to them, and so I'm actually describing here how your final grade is calculated. Multiply each value by its weight to get a point value for each of them, and then add all those point values together. Remember, that's how we came up with that GPA. And then when we then add up all the weights together to get a sum of all the weights, and that's the number that we divide our previous sum by. So we add up all those points and get a total amount of points. We then add up all the weights, get a total amount of weights, and it's points divided by weights. Total points divided by weights. So that's the major way in which this departs from the non-weighted mean, in which you divide the sum just by the number of numbers, as you recall. Here we're dividing it by the total of all the weights. And then what do we do if we've got the data being summarized into a series of frequency intervals, perhaps for privacy reasons or some other reasons there? How do we find the mean there? We first of all list the midpoint of each one of those class intervals there. We're going to use those to provide a sort of a proxy value for each one of our data points. And after tallying all the frequencies, in other words, tallying all the people or all the data values that exist inside of each one of these intervals, then we multiply each midpoint by the tally that's in that class interval, and we add up all those point totals together, and then we want to divide by the number of numbers once again, this is another way of saying that, adding all the frequencies together. Well, that's all of the tallies together. That would be all the numbers added up together. So it's really, you're dividing here by the number of numbers, just like when you were doing a non-weighted average. So yes, dividing the point total by the number of numbers, the frequency total. So I'm taking a look here at 2 different sets of data, and we've already seen these 2 different we've already seen two different ways in which we can summarize the central tendency for each one of these data sets here. They both have means that are 30.4, and they both have medians of 29. So we've concluded here how to all the three different measures of central tendency here. But I'm noticing here those two sets of data look very, very different, even though they have the same median and the same mean. Perhaps you can see that looking at the first value and the last value, because they've been placed in numerical order from smallest to largest here. You notice anything different between those two sets of data here? Hopefully what you can see is that the second set of data is far more spread out than the first set of data. So they have the same measures of central tendency, but they're going to have very different statistics when it comes to measures of dispersion. And you can start to see that already as we start to define some of these things. The smallest value in the first set of data there is 26, the largest value is 36, and so our first measure of dispersion is something that's just called the range. We take the biggest one minus the smallest one, the maximum minus the minimum, and we get the range there. In this case, 36 minus 26 is just 10. In stark contrast to what we see on the right here, the smallest number is 2, the largest number is 56, the range is much bigger now, it's 54, so a much bigger range with the data that's on the right here. Now let's explore this further with another set of data here. I'm showing you a set of data that has been placed in numerical order there. The smallest one, 63, is on the far left. The largest one, 97, is directly above my head. And as you can see here, the minimum and the maximum are immediately visible there, the minimum being 63 and the maximum is 97. The median, which we already know how to calculate, is the middle number there, and that has a value of 84. Now, in addition to that, we can also define two other values that start to define how dispersed the data is. If we just take a look at the data that's on the left-hand side of the median, so the lower set of data, we can define the median of just that lower half. So the lower quartile there is defined as 76.5. It's the average of those two data points that are in the center of that lower portion. In the upper portion, closer to me here, we can define another median of that upper half that we call the upper quartile. That's 90.5. And so let's talk about how widely dispersed those values are here. So first of all, the difference between the minimum and the maximum, that's 97 minus 63. That's a range of 34. So range is one of our measures of dispersion. We can also define another measure of central tendency here, which is not very popular, but sometimes it's used. It's called the mid-range. So if you take the maximum value and you take the minimum value and you find the average of those two, that gives you something that's called the mid-range. It's not very popular, it's not used very often, but it is used sometimes, and so that's how it's defined there. In addition to this, if we take a look at the lower quartile and the upper quartile and find the difference between those two, we get 90.5 minus 76.5 for a value of 14. We call this the inter-quartile range. It's the range within it's actually the difference between the lower quartile and the upper quartile. So think about where that lower quartile and the upper quartile exist. They're actually the half the data is in between those two locations, right? Because it's 1/4 directly above my head, 1/4 between the upper quartile and the median, another quarter between the median and the lower quartile, another quarter between the lower quartile and the minimum. So two of those quarters are on either side of the median there. So the lower quartile and the upper quartile together circumscribe the just half of the data there. Half the data is in between that upper quartile and the lower quartile. And so it's kind of interesting to see what the range is of the innermost half of the data. And so in this case, the range isn't 34, it's somewhat smaller, it's just 14. So let's summarize what we found so far here. To find the range, and that's easy. You just take the largest value and subtract the smallest value. You find the difference between the maximum and the minimum. That's your range. The mid-range, which is actually technically a measure of central tendency, not really a measure of dispersion, but nevertheless, you just find that by finding the mean of the highest and lowest values. To find the quartiles, well, you first find the median of the data set, and that divides the data set into two halves, one lower and one higher. You then find the median of each half, the middle of each half, and that effectively divides the data set into 4 quarters. And the median of the lower half of the data is the boundary for the lower quartile, and the median of the upper half is the is the boundary for the upper quartile. So how do you find the interquartile range? It's just the difference between the upper and lower quartile value there. So the difference between the upper quartile boundary and the lower quartile boundary gives you the interquartile range. Lastly, percentiles. Now, some of you might have seen this if you ever took standardized tests as a child and got some results back in which the scores were oftentimes described in terms of percentiles. And if you saw something like that, then most likely what was being done is your score was being compared by the hordes of other scores that were received from all the other students, perhaps statewide or even nationwide, who took the exam. The percentile describes, in that case, the percent of students who did not do as well as you did. In other words, the percentage of all the test scores that were lower than yours. If the value is very low, then you did better than only a small number of students. If the value was very, very high, a high percent, like 98 or 99, then you did better than the vast majority of all the other students. So how do we find these kinds of percentiles here? Well, let's say that we're given here a set of test scores from 63 all the way up to 97. How do we find what those percentiles are? So finding the 25th percentile, actually some of these are actually pretty straightforward. What do you think would be the 50th percentile? Well, that's the point at which half the data is higher than that value and half the data is lower than that value. We actually have another term for that. We call that the median. What would be the 25th percentile? Well, that's the value in which half of the lower half of the data is less than that, and the other half of the lower half of the data is greater than that. So it's that actually turns out to be the lower quartile, the boundary of the lower quartile. What is the 75th percentile there? Well, if we're just looking at the upper half of the data, that's the median of the upper half, isn't it? That's the boundary for the upper quartile there. So that's the value at which 3/4 of the data is less than that value, and only 1/4 is greater. So, to some extent, working with percentiles is something you've already done before. The median is the 50th percentile. The lower and upper quartiles are the 20th, 25th, and the 75th percentile. And what would be the minimum and the maximum? Well, the minimum would be the 0th percentile. There's nothing that's less than the minimum. And the maximum would be the 100th percentile, because everything is less than the maximum. So, the way that we would do this for other percentiles, say like the 80th percentile or the 90th percentile, it's important for us to, first of all, number all of our data values from 1 to 25. They've just been numbered in sequential order here. And what we do is we use this formula here. So what I'm showing you here is 25 over 100. So we're first of all looking at the 25th percentile. So 25 over 100, that's 25%, times the number of data points that we're working with. As you can see, that's 25. So 25 over 100 times 25. If you put all of that together, you get a value of 6.25. Okay, well, that's supposed to define which number to look at here, and we actually round that up to 7. So it's the 7th data element that is actually our 25th percentile there. So the 7th data element is 77, so our 25th percentile is 77. So if you got a score of 77 on the exam, you got the 25th percentile. How about the 80th percentile? Well, we're just going to use the same formula again. Now it's 80 over 100 times the 25 data values there, and we get a value of 20. There's no need to round this time. The 20th data value is 91. So the 80th percentile of this distribution of data is 91. And lastly, if we're finding the 90th percentile, 90 over 100 times 25 is 22.5. We round that up to 23, and the 23rd, that should say, data item is 93. So the 90th percentile is 93. So if you got a value of 93 on the exam, take heart, you got the 90th percentile on the exam. So to summarize for this, to find the percentiles, first thing you do is we do our familiar thing of arranging the data items in ascending order from smallest to largest, and then you number them, starting with 1. Solve this equation for n, where p is the percentile number that you're given, and capital N is the number of data points that you have. Remember, in our previous example, that was 25. We were working with 25 data values. So capital N there is 25. And then you solve that equation there. Now, if the value that you get is not a whole number, you always round up to the next whole number, and then that nth data item there that you get, look at the value of that data item, and that's your percentile that you're looking for. Now, the last measure of dispersion that I'm going to cover, as it turns out, is actually the most commonly used, the most popular, and it's called the standard deviation. Now, it's outside the scope of this course for me to discuss the full theoretical development of how the standard deviation is used and its relationship to the bell curve. There are actually plenty of videos on YouTube if you just do a search on standard deviation or the normal distribution or the bell curve, in which you can get a lot of development there. And its relationship, the relationship that the standard deviation has to the normal distribution or the bell curve. What I'm here to cover is really just how do you calculate the standard deviation given a set of data. And this is something that you'll be tested on in the exam. You'll notice here that I've created for you a chart for going through the procedure of taking a set of data and calculating the standard deviation. I'll give you the same chart on an exam. You should also see something like that on your activity sheet. Really, the process has sort of been placed into a template here for you. So you're basically just filling in the boxes as you go through to calculate the standard deviation. All right, so the first thing that we do here is to take a look at our data points. We have 4 data values. There's 38, 43, 45, and 44. All right, so the first thing that we do is place those data values near the top of that second column there under data. They don't have to be placed in order from smallest to largest or anything like that. They can just be basically just placed in there. And the first thing we're going to do is add all of those data values together to give us 170. Why are we doing that? Because we're calculating the all-familiar mean by dividing it then by the number of data values, that's 4, to give us a mean of 42.5. That's familiar territory, hopefully. But now we're into unfamiliar territory. What we're going to do is to calculate what are called deviations, and there's one deviation to be calculated for each data value, and it's where we take the data value, in this case 38, and we subtract off the mean. So what we're getting here is the distance that that data value departs from the mean. So how far away from that sort of center of mass, so to speak, that that data value actually resides. In this case, 38 minus 42.5, that's a negative 4.5. This data value is smaller than the mean, and some of the others will be positive because they're larger than the mean. So what we're going to do now is do the same thing with the other data values. 43 minus 42.5, that's 1/2, 0.5. 45 minus 42.5, that's just 2.5. And lastly, 44 minus 42.5, that's just 1.5. So far, so good. The next thing we have to do is to take each one of those deviations and multiply each one by itself. We have to square it. And so we're going to be filling in this last column here in which we are placing squared deviations in here. In the first one, it's negative 4.5 times negative 4.5. That gives us 20.25. The second one, 0.5 times 0.5, a half times a half is a fourth, 0.25. The third one, 2.5 times 2.5, that's 6.25. And lastly, 1.5 times itself is 2.25. Now, just like when we were adding up all the data values together to get the sum and then get the mean, we're going to do something similar in this column now, except that instead of adding the data values up, we're going to be adding these squared deviations together. So 20.25 plus 0.25 plus 6.25 plus 2.25, we're going to add those up, in this case to get a nice even number, 29.00. That is the sum of all the squared deviations. What do we do next? Well, we divide it. We're actually getting a kind of mean here, but as it turns out, for reasons that I don't have time to go into here, we actually divide it not by 4, but we actually divide it by 1 less than 4. We divide it by 3. And the result here is that we get something that's called the variance. This is a measure of what the sort of average square deviations are from this central value here, this mean. And that's the value here that we have, 9.67. That's the variance. We're almost home. All we have to do now is take the square root of the variance, and that gives us the standard deviation. All right, so in this case, we just filled in this chart, first of all, by placing the data values where they're supposed to be, calculating the mean of those data values, then creating deviations by subtracting off the mean from each one of those data values. Then we have to square each one of those deviations, add up all those squared deviations, divide by the number of numbers minus 1, not 4, but 3. Once we divide by 3, then we have the variance, and we take the square root of the variance to get the standard deviation here. So to summarize how we do this, to find the standard deviation, we first find the mean of the data. You saw us do this here. Then we found the deviations of each data point from the mean. So you can see here, I'm symbolizing the mean with an X with a little bar over top here. So we're finding out for each data value X sub I prime. If this helps you understand, then that's fine. If not, then just ignore this here. We're finding the deviation of each data point from the mean. That's xi prime. That's equal to x sub I, the original data point, minus the mean value here. That's x bar. And once we have each one of those deviations, then we square each deviation. So that's x sub I prime squared now. And we divide the sum of those squared deviations by 1 less than the number of data items. So you saw that in the previous slide there, not 4, but 3. We divided by 3. This is called the sample variance. So you can see here, this is just a symbolic way of describing this. We squared all those deviations, we added all of those up, and we divided those not by n, but by n minus 1, and that gives us the variance. And then lastly, we just take the square root of that variance to get the standard deviation. So take some time to do this one on your own here. I've given you a different data set to work with, but it's the exact same chart. So take some time here to calculate the standard deviation of this data set here. 45, 63, 87, 91, those are your data values. Take some time to do that. Welcome back. Well, hopefully this procedure was pretty familiar here. We took our 4 data points, we added them together to get the sum of 286, divided then by 4 to get a mean of 71.5. We then subtracted each one of those data values from that mean to get deviations, negative 26.5, negative 8.5, or positive 15.5, and positive 19.5. You'll notice actually that squaring all of those deviations makes it so that some of them are not negative and some of them are positive. They're all positive now when we square them. So you can see those are all positive numbers now in the square deviations column. 702.25, 72.25, 240.25, and 380.25. When we add all those together, we get 1395, and remember, we divide by 3 this time to get a variance of 465, the square root of which is 21.56. So that's our standard deviation there. Well, we've covered an awful lot of material here. We've covered the measures of central tendency, mean, median, and mode. We've also covered some measures of dispersion as well. The interquartile range, the range, as well as now the standard deviation. So go through your activity sheet and make sure that you highlight all of the things that are most important, which will help you to study most efficiently and effectively for the upcoming exam. See you next time.